In this video, we will be going over how to identify the presence of molecular dipole moments. But before we go into that, we need to talk about electronegativity in order to fully understand dipole moments. In a covalent bond, electrons are shared between two atoms. When the atoms are the same, such as in an H2 molecule, the electrons are shared equally, meaning the electrons spend the same amount of time around each atom. Right? So if we draw a H2 molecule, the electrons spend the same amount of time in between or around each hydrogen atom. So half the time you'll find the electrons around the left hydrogen, and half the time you'll find the electrons around the right hydrogen. We call this electron density, which is the probability of finding an electron in a particular region of space. The electron density is even in this case, meaning the probability of finding the shared electrons in the region of space around each hydrogen atom is the same. So why is this? Electronegativity has to do with electron affinity, which is the energy needed to remove an electron from an anion. So an anion is an ion with a negative charge, meaning it has one or more extra electrons attached to it. For instance, atoms tend to achieve an octet electron configuration, which means having 8 valence electrons around it, since this is the most stable state. So an atom with 7 valence electrons, like fluorine, for instance, so an atom like fluorine that wants to achieve an octet will borrow an electron from somewhere else, say from another atom with only 1 valence electron, like sodium. So sodium is anxious and willing to give up its electron to achieve its own octet, right? So sodium will give up its electron to this fluorine, and then now fluorine will become an anion, which is a negatively charged atom because it accepts an extra electron from the sodium. So both atoms help each other achieve its goal. So now fluorine becomes an anion, a negatively charged atom, and is now in its most stable state. Because fluorine is now so stable, it's going to have a hard time to remove that electron from it, right? Fluorine's not going to give this electron up so easily because it's so stable now. So it wants to maintain its stability if it can. So atoms that have a tendency to pick up electrons, such as atoms to the right of the periodic table, such as elements in group 6 and 7, tend to have a high electron affinity, since they have the most to gain from accepting an electron. This brings us back to electronegativity, which was our original topic. And this is just the ability of an atom to attract towards itself electrons in a bond. As we mentioned earlier, electronegativity and electron affinity are related. The higher the electron affinity, the higher the electronegativity. And so the difference being that electron affinity has to do with a single atom, where electronegativity has to do with atoms in a bond. So going back to our H2 molecule, our hydrogen molecule to the left, since our atoms are identical, they have identical electronegativity, or identical ability to draw or attract the electrons towards itself. However, in a hydrogen fluoride atom, a hydrogen fluoride molecule, such as this over here, in a hydrogen fluoride molecule, the situation is different. Fluorine has a high electron affinity and therefore has a high electronegativity. It will draw the two electrons in the covalent bond. So these two electrons right here. It will draw these two electrons towards itself, right? So it'll draw them in this direction towards itself and away from the hydrogen. And thus the electrons will spend most of the time in the region of space around the fluorine atom. And so therefore fluorine will have a higher electron density than hydrogen. We call bonds of this nature polar covalent bonds, or just polar bonds. Polar bonds. And so if you think of the hydrogen atom and the fluorine atom as two ends or poles of the bond, much like the north and south poles of the Earth, the electron density will be concentrated at the fluorine pole of the bond. So now that we have a decent understanding of electronegativity, let's move on to dipole moments. So in a covalent molecule with a polar bond like hydrogen fluoride, the electron density shifts from hydrogen to fluorine, since fluorine is more electronegative than hydrogen. So the electron density shift is represented by an arrow above the Lewis structure, like so. So if we draw our hydrogen fluorine atom, once again, over here, we draw an arrow above the Lewis structure with a line down the middle, and that's going to be how we represent electronegativity. Or if we want to, we can also represent electronegativity like this. So let's go ahead and redraw our bond. Right, this line just stands for two electrons in a covalent bond. So we can draw a delta plus or a delta minus. And what this means is that since the so basically delta means partial charge. Since the probability of finding the electrons in the bond is higher in the region of space around fluorine, which means it has a higher electron density, it has a partial negative charge, right? It's partially negatively charged. Whereas the hydrogen has a partial positive charge, right? For the same reason. And so the dipole moment measures the polarity of the bond. In other words, it measures how unevenly the electrons are shared in a bond. Molecules containing two atoms of different elements have unequal sharing of electrons, and therefore are polar bonds, and thus have dipole moments. Molecules having two atoms of the same element, such as H2, like we just mentioned, O2, or F2, right? So these have equal sharing of electrons because they are made up of the same atom. And so So they're gonna be nonpolar molecules, and therefore have no dipole moment at all. So if you remember, dipole moments measure polarity, right? If there's no polarity, then there's no dipole moment. Since dipole moments measure the polarity of a bond, it has both a magnitude and a direction, making it a vector, right? So this arrow up here is basically a vector, right? It's pointing in the direction of the fluorine molecule. The fluorine atom. So the dipole moment measures the direction along the bond that the electrons are being pulled to, and how strongly they're being pulled, right? So because fluorine is highly electronegative, in fact, it's the most electronegative atom, this bond is going to be highly polar, and the electrons are going to be strongly pulled towards the fluorine. So this dipole moment is going to have a very high magnitude, and it's also going to have a direction along the bond, and it's going to be pointing towards the fluorine atom. And so in a molecule with more than two atoms, and therefore more than one dipole moment, we have to add dipole moments together, giving us the overall or net dipole moment of the whole molecule. So to add dipole moments, we have to add their vectors, right? And so let's take carbon dioxide, for example. So let's say we have CO2. And let's go ahead and draw its Lewis structure, right? So the Lewis structure of CO2 is going to look like this, with oxygen in the center, and it's going to be double bonded to two carbon atoms, one on each side. And then there's going to be, actually, this is actually backwards. So carbon is going to be in the center, and then the carbon is going to be double bonded to two oxygen atoms, one on each side, right? And then each oxygen is going to have two pairs of electrons, so two lone pairs. And so this is carbon dioxide. And since we have two bonds with different atoms, we have two dipole moments, right? And since oxygen lies to the right of carbon on the periodic table, it's going to be more electronegative than carbon is. And so the dipole moment will look like this. So there's going to be an arrow pointing from the carbon to the oxygen on the left, right? Because that's going to be the direction of the polarity of this bond, this particular carbon-oxygen bond. And for this carbon-oxygen bond, there's going to be another arrow pointing to the right towards the oxygen because it's more electronegative, and therefore this oxygen is going to draw the four electrons in this double bond towards itself, right? So the electrons are going to spend more time around these two oxygens than they are going to spend around the carbon in the center. And so therefore we're going to have one arrow for each bond. Now to add the vectors, we just connect the vectors head to tail, and then draw a new vector from the tail of the first vector to the head of the second vector, giving us a new vector called the vector sum. So now let's call this vector vector 1, and then let's call this vector vector 2. So how do we add vectors? So let's do an example. So let's say we have one vector pointing to the right and then one vector pointing down. Let's call this vector 1, and then let's call this vector 2. So to add vectors, I would take vector 1 and connect it to the tail of the second vector, vector 2, and then draw a new vector from the tail of vector 1 to the head of vector 2. So I will take this first vector and then connect the tail of vector 2 to the head of vector 1, and then I would draw a new vector from the tail of 1 to the head of 2, like this, right? And so that's going to be our vector sum, right? That's going to be the sum of both of our vectors. And so in the case of carbon dioxide, we have two dipole moments of equal magnitude but opposite direction. So to add their vectors, we simply repeat the same procedure. We take the first vector, which is vector 1. Then we take the other vector, which is vector 2, and then connect them head to tail. So here's our second vector, and now we just connected them head to tail. So the tail of the first is exactly on top of the head of the second, and vice versa, right? They lie exactly on the same point in space. So drawing a line from the tail of the first to the head of the second is impossible, right? We need 2 points to make a line, but we only have one. And so therefore the vector sum has no magnitude or direction, meaning the overall or net dipole moment is going to be 0, right? So this shows us that even if polar bonds are present in a molecule, it can still have no dipole moment.